In February 2022, a 400-foot cargo ship left the port of Tokyo carrying over 100 containers of automotive parts destined for a factory in Yokohama. The journey was supposed to take about 240 nautical miles along Japan's eastern coast. Nothing unusual about that, except for one small detail. There was no one steering the ship, no captain on the bridge, no navigator plotting the course. The entire journey was controlled by artificial intelligence. This wasn't some small experimental vessel or a prototype in a test facility. This was a real commercial cargo ship, carrying real cargo, operating in one of the busiest shipping lanes in the world, with nobody touching the controls. And what makes this so fascinating is that, by all accounts, this technology should not be ready yet. Autonomous cars are still struggling to navigate city streets after decades of development and billions in investment. Self-driving trucks are only just beginning to operate on highways under carefully controlled conditions. But shipping companies are already deploying autonomous vessels in open ocean, carrying millions of dollars of cargo with zero human intervention. The technology behind these ships is advancing faster than anyone expected, and it's going to completely transform an industry that's looked basically the same for over a century. To understand this, you first have to understand why ships are actually easier to automate than cars. This sounds counterintuitive because ships are massive, complex, and operating in a dynamic environment with waves, wind, and weather. But think about the actual navigation problem. On a highway, a self-driving car has to deal with thousands of variables every second. Other cars changing lanes, pedestrians crossing streets, traffic lights, stop signs, construction zones, cyclists, emergency vehicles. The environment is dense, chaotic, and constantly changing. One mistake, and you have a fatal accident. Ships, on the other hand, operate in a much simpler environment. The ocean is mostly empty. There are no lanes to stay in, no traffic lights to obey, no pedestrians to avoid. The nearest other vessel is often miles away. And ships move slowly, typically 15 to 20 knots, which gives autonomous systems plenty of time to detect obstacles, calculate trajectories, and adjust course. A container ship traveling at 18 knots is moving at about 20 miles per hour. That's slower than most cars on city streets. When you're moving that slowly, and the nearest obstacle is 3 miles away, you have minutes or even hours to make decisions, not milliseconds. But there's a second reason ships are easier to automate. They're already heavily computerized. Modern container ships have been using sophisticated autopilot systems for decades. These systems can maintain course, adjust for wind and current, and even execute basic collision avoidance maneuvers. What's happening now isn't inventing automation from scratch. It's upgrading existing systems with AI and removing the human backup. A modern ship already has GPS, radar, AIS, automatic identification system, weather sensors, sonar, and dozens of other instruments constantly feeding data into onboard computers. The ship already knows where it is, where every other ship around it is, what the weather conditions are, and what hazards exist. The autonomous technology is just processing that data and making decisions without human input. So, what exactly is the technology that makes this possible? It starts with sensor fusion. An autonomous ship isn't relying on a single sensor or camera. It's combining data from multiple independent systems to build a complete picture of its environment. The ship has marine radar that can detect other vessels, land masses, and obstacles up to 20 or 30 miles away. It has AIS receivers that pick up transponder signals from other ships, telling it exactly where they are, what direction they're heading, and how fast they're moving. It has LiDAR systems that use lasers to map the immediate surroundings in 3 dimensions. It has optical cameras with computer vision algorithms that can identify navigation markers, buoys, coastlines, and potential hazards. And it has sonar systems that can detect underwater obstacles or shallow water. All of this data flows into a central AI system that fuses it together into a unified picture of the world. If the radar shows a ship 5 miles ahead, the AIS confirms it's a tanker heading east at 12 knots, and the cameras can visually identify it. The system has very high confidence that vessel is exactly where it thinks it is. This redundancy is critical because no single sensor is perfect. Radar can be fooled by weather, cameras can't see in fog. AIS can be turned off or spoofed, but when multiple independent sensors all agree, the system can be confident in its understanding of the environment. The next layer is path planning and navigation. This is where the AI decides not just where the ship is, but where it should go and how to get there safely. Modern autonomous systems use something called dynamic path planning. The AI doesn't just plot a straight line from point A to point B and follow it blindly. It constantly recalculates the optimal route based on changing conditions. If a storm is developing ahead, the system might adjust course to avoid it. If another ship's trajectory creates a potential collision risk in 30 minutes, the system might slow down or alter course slightly to maintain safe separation. If currents are pushing the ship off course, the system compensates automatically. These systems use machine learning models trained on millions of hours of real voyage data. Engineers feed the AI historical data from thousands of previous voyages. What did experienced captains do when they encountered this specific combination of weather, traffic, and ocean conditions? The AI learns patterns. When to slow down, when to change course, when to wait for better conditions, when to push through. It's essentially learning from the collective experience of thousands of human captains, compressed into algorithms that can make decisions in real time. But here's where it gets really interesting: collision avoidance. This is the most critical safety system because it's the difference between a successful voyage and a multi-million-dollar disaster. Autonomous ships use something called SOL regs, the international regulations for preventing collisions at sea. These are the rules of the road for ships, established in 1972, that determine who has right-of-way in different situations. For example, if two ships are approaching head-on, both should alter course to starboard, right. If two ships are crossing paths, the vessel that has the other on its starboard side gives way. The challenge is that SOL regs were written for human captains making judgment calls, not for algorithms making binary decisions. There's ambiguity and room for interpretation. So, autonomous systems have to not only follow SOL regs, but also predict what other ships, which might have human captains, are going to do. The AI uses predictive models that analyze other vessels' speed, heading, and behavior patterns to forecast their likely actions. If a ship is approaching on a collision course, the system calculates, are they going to alter course as required by SOL regs, or do I need to take defensive action? It's essentially game theory applied to maritime navigation, and this is where autonomous ships actually have an advantage over human-crewed vessels. Humans get tired, distracted, or complacent. About 75% of maritime accidents involve human error. Autonomous systems don't get fatigued after a 12-hour watch. They don't lose focus. They're constantly monitoring 360 degrees simultaneously, while humans can only look in one direction at a time. In testing, autonomous collision avoidance systems have response times measured in milliseconds, compared to seconds or even minutes for human crews to recognize a threat, communicate, and execute a maneuver. Now, let's talk about the actual ship control systems. Once the AI decides what maneuver to make, it has to physically control the vessel. This involves three primary systems: propulsion, steering, and ballast. Modern ships are already fly-by-wire, meaning controls are electronic, not mechanical. When you turn the wheel on a modern ship, you're not physically moving the rudder. You're sending an electronic signal to hydraulic actuators that move the rudder. This makes automation relatively straightforward. The autonomous system just sends the same electronic signals a human would send. But ships are not like cars. They have massive momentum and inertia. A container ship traveling at 20 knots can take several miles to stop even with engines in full reverse. Turning takes time. A large vessel might need a half mile or more to complete a 90-degree turn. So, autonomous systems have to think ahead, predicting how the ship will respond to control inputs and planning maneuvers well in advance. The AI uses physics models that account for the ship's mass, speed, hydrodynamics, wind resistance, and current conditions to predict exactly how the vessel will respond to different control inputs. The ballast system is also critical. Ships adjust their weight distribution by pumping water into or out of ballast tanks to maintain proper trim and stability. Too much weight forward and the bow sits low in the water. Too much aft and the propeller might not be fully submerged. Autonomous systems monitor the ship's trim constantly and adjust ballast automatically to maintain optimal performance and fuel efficiency. This is something human crews do manually at intervals, but autonomous systems can do continuously, resulting in measurably better fuel economy. Then there's engine management. Modern ship engines are incredibly complex, enormous diesel engines the size of buildings that have to be carefully monitored and maintained. Autonomous systems track engine temperature, fuel consumption, oil pressure, vibration, and dozens of other parameters. They can detect anomalies that might indicate developing mechanical problems. A slight increase in vibration might mean a bearing is wearing out. A small change in fuel consumption might indicate a clogged fuel injector. The system can alert shore-based engineers to problems before they become critical, allowing maintenance to be scheduled proactively instead of reactively dealing with breakdowns at sea. But there's one technology that makes all of this possible, and it's something most people don't think about: satellite communications. Autonomous ships aren't operating in isolation. They're constantly connected to shore-based control centers via satellite links. These control centers monitor the vessel in real time, receiving updates every few seconds on position, status, sensor data, and system health. If something unexpected happens, a system malfunction, unusual weather, a complex traffic situation, shore-based operators can intervene remotely. Think of them as air traffic controllers for ships. The vessel operates autonomously 95% of the time, but humans are always watching and can take control if needed. This creates a hybrid model that's actually more practical than either full autonomy or traditional crewed vessels. Instead of needing 20 to 25 crew members living on board for weeks or months at a time, you might have 2 or 3 shore-based operators monitoring multiple ships simultaneously from an office building. This dramatically reduces labor costs, which can represent 30 to 40% of a ship's operating expenses, while maintaining human oversight for safety-critical decisions. And shore-based operators work normal shifts, go home at night, and don't deal with the physical and psychological challenges of months at sea. Several companies are now operating commercial autonomous vessels. Yara Birkeland in Norway is a fully electric autonomous container ship operating on short coastal routes. It's designed to replace 40,000 truck trips per year with zero-emission shipping. Kongsberg Maritime and Masterly are developing autonomous ferries for Norwegian waters. In Japan, companies like NYK Line and Mitsui OSK Lines have conducted successful autonomous trials on commercial routes. In China, the government has invested billions in autonomous shipping development and established dedicated testing zones. These aren't science experiments anymore. They're real commercial operations generating real revenue. But there's a catch, and it's a big one: regulation. The International Maritime Organization, IMO, sets global standards for ship safety, and current regulations assume ships have crews on board. Things like bridge layout, emergency procedures, life-saving equipment, all of this is designed around having humans present. Autonomous ships don't fit into this regulatory framework. Who's legally responsible if an autonomous ship has an accident? The owner, the software developer, the shore-based operator? What certification is required for autonomous systems? How do you prove they're safe? These are not hypothetical questions. They're active legal debates happening right now. Different countries are taking different approaches. Norway is aggressively pushing autonomous shipping and has created special regulatory zones where autonomous vessels can operate under relaxed rules to test and prove the technology. Japan has done similar pilot programs. Singapore, which operates one of the world's busiest ports, is investing heavily in autonomous vessel research and building infrastructure to support them. But most countries, including the US, have been more cautious. The U.S. Coast Guard has regulations that effectively require ships in American waters to have licensed officers on board, which makes autonomous operation legally impossible without regulatory changes. There's also the cybersecurity problem. An autonomous ship is essentially a computer connected to the internet, which makes it a potential target for hacking. If someone gains unauthorized access to a ship's control systems, they could theoretically commandeer the vessel, change its course, or even cause a collision. This isn't theoretical paranoia. In 2017, the NotPetya cyber attack crippled Maersk's entire global operations for weeks, and that was just attacking their IT systems, not ship controls. If autonomous ships become widespread, they'll need military-grade cybersecurity, and even that might not be enough against sophisticated state-sponsored hackers. Then there's the human cost. The global shipping industry employs over 1.6 million seafarers. These are skilled, well-paid jobs that provide stable careers for workers in many developing countries. If autonomous ships eliminate the need for onboard crews, what happens to those workers? Some might transition to shore-based positions. This creates political resistance to autonomous shipping, particularly from maritime unions and countries whose economies depend on seafaring employment. But despite these challenges, the technology is advancing rapidly because the economic incentives are massive. Labor costs represent $3,000 to $5,000 per day for a typical cargo ship crew. Eliminate the crew, and you save over $1 million per year per ship. Scale that across a fleet of 100 ships, and you're saving $100 million annually. That's enough to justify massive technology investments. There are also safety benefits. 75% of maritime accidents involve human error, so removing humans from hazardous environments could save lives. And there are efficiency gains. Autonomous systems can optimize routes and fuel consumption in ways human crews simply can't match, potentially reducing emissions by 10 to 15%. The technology is also improving exponentially. 5 years ago, autonomous ships were science fiction. Today, they're operating commercially on short routes. In 5 more years, we might see fully autonomous vessels on transoceanic routes. The AI systems are getting better as they accumulate more training data. Sensor technology is getting cheaper and more reliable. Satellite communication bandwidth is increasing while costs are dropping. And regulatory frameworks are slowly adapting to accommodate the new technology. But we're also seeing a bifurcation in the industry. Long-haul ocean shipping, the massive container ships crossing the Pacific, will probably remain crewed for decades because the regulatory hurdles are enormous and the economic case is less clear. Those ships already have small crews relative to their size. But short-haul coastal shipping, ferries, harbor operations, and specialized vessels are already going autonomous because the routes are predictable, the regulatory environment is friendlier, and the business case is compelling. There's also a middle ground emerging: reduced crew vessels. Instead of eliminating crews entirely, some companies are reducing crew size from 20 to 25 people down to just 5 to 10. With autonomous systems handling routine operations and humans present for complex situations and emergencies, this provides most of the cost savings while maintaining a human safety backup and satisfying regulators who aren't ready for fully crewless ships. The irony is that autonomous cargo ships might become commonplace before autonomous cars do. Ships operate in a simpler, less regulated environment with fewer obstacles and more time to react. The technology is already proven in commercial operation. The economic case is clear, and despite the regulatory challenges, it's easier to get approval for an autonomous ship operating in international waters than for a self-driving car operating on public roads where pedestrians are present. So, what does the future look like? Within 10 years, we'll likely see hundreds of autonomous vessels operating globally, primarily on short and medium-range routes. Within 20 years, a significant percentage of the global fleet could be autonomous or minimally crewed. Shore-based control centers will manage fleets of ships like drone operators manage UAVs. Ships will be more efficient, safer, and cheaper to operate. But we'll also see major disruptions to maritime employment, ongoing debates about liability and regulation, and new cybersecurity threats. The technology behind autonomous cargo vessels isn't just about replacing human crews with computers. It's about fundamentally reimagining how global shipping works. It's about creating a system where machines handle routine operations with superhuman consistency while humans focus on strategic decision-making and handling exceptional situations. It's the same pattern we've seen in aviation, where autopilot systems now handle most of the flying, while pilots manage the overall flight. The difference is, shipping is going further faster, because the operational environment is less complex and the economic incentives are more compelling. What do you think? Are autonomous cargo ships the future of global trade, or are we moving too fast with technology that's not ready? Let us know in the comments below.